query locally correctable codes, and this will be working over finite fields. So let P be any prime, we will be working over FP, and this is joint work with Arnab and Zev and Amish Pilka. Okay, so let me just make the definitions. So we'll say that so an error correcting code is a linear two query LCC over FP. So if it's if you have a linear subspace of FP to the n, so so it's of length n. So this is, so C is a linear subspace. Say its dimension is D. So it's going to be a locally correctable code which say corrects from D fraction errors. If suppose you have some little c which is an element of the code, and you have some element of FP to the n, so whose distance from C is small. So suppose you know that the distance of little r and C is at most delta n. Okay, so you can think of R to be a corrupted version of a code word. You have a true code word, it has been corrupted in some small fraction of the coordinates. Then we say it's locally correctable if you can still correctly recover the true value of each coordinate of C. So this is a two query LCC if for all coordinates I we can with an algorithm which will with high probability recover the ith coordinate of C. So for any coordinate you can recover the true value with at most 2 queries to R. Okay, so you're given a true code word, you're given access only to a corrupted version of it, and with very, very few queries to the corrupted version, you want to with high probability be able to recover any coordinate of the original code word. So if the code has this property, I call it a 2 query locally correctable code. And so I'll be only talking about linear correcting code, so C is going to be a linear subspace, and it's not hard to show that whenever you have such an algorithm which will recover every coordinate by looking at 2 other coordinates, this recovering process also must be a linear process. So suppose you queried the jth and kth coordinate to recover the ith coordinate. So this decoding must be linear. And if you can use the jth and kth coordinates to recover the ith coordinate, so say alpha, it must be that alpha, suppose you use alpha rj plus beta rk was your choice for Ci. This must in particular hold even when rj was Cj and rk was Ck, when they came from the true code word. It must be that alpha Ck Cj plus beta Ck is also Ci. Yeah, that's it.
So this is a picky point, but are you only talking about non-adaptive algorithms, or is this also true for adaptive?
So I don't think it matters very much, but for now, say it's non-adaptive. But I don't think it really matters. Okay. So it's not adaptive. I'm going to pick 2 coordinates and take the linear combination and call that Ci. So and since I don't know so I've just seen 2 coordinates. I don't know what the underlying code word is, or I don't know anything about it. This relation must hold for all C. If I'm going to use the decoding to correct it for one code word. Okay, so if I'm going to query some 2 coordinates to recover the value of some coordinate, that means for all code words in the code, it must be that these 3 coordinates are linearly dependent. So in particular, so if you look at so the entire linear subspace must have this property. So let's look at a matrix. Let's construct a matrix G whose rows form a basis for C. So this is, say, a D by n matrix. Okay, so this is a d-dimensional subspace. I take a basis for it, and write each basis element as a row of this matrix. So suppose, now look at the columns of this matrix. So again, so each code word is some linear combination of the rows of the matrix, and in particular, so every C in C looks like the form some m times G. You take some d dimensional, some vector of length d multiplied by G, and you get a code word. So the code is just the image of this linear transformation. And again, if you use Cj and Ck to recover Ci, it must be that in this matrix the ith, jth, and kth columns are linearly dependent as vectors. So in particular, so it must be that Vi is in the span of Vj and Vk. Okay. So, and in particular, you must, so again, to recover I, you must have at least two elements, Vj and Vk, such that Vi is in the span of Vj and Vk. In fact, you must have many of them, because you are allowed to corrupt a delta fraction of the coordinates and still be able to recover the code. So not only must you have the Vi be in the span of one pair of vectors from this matrix, you must have Vi to be in the span of many, many pairs of vectors. So this is the requirement for locally correctable codes. So, and in fact, so Vi is in the span of many Vj, Vk. It will be in the span of at least many disjoint. If they're going to be delta, if it's going to be recoverable from delta n fraction of errors, there'll be at least delta n over 2 disjoint, in fact, Vj, Vk, which will recover it. So at least delta n over 2 disjoint pairs. And this, we want this to happen for every I. So for every vector Vi, there must be many, many disjoint pairs who says that Vi is in the span of these pairs. Okay, so these are the codes we want to look at and study. And so the main result I'm going to show is that if you have any such two-query LCC, then the length of the code, so the n must be much, much larger than the dimension of the code. So the main thing we're going to show is that n must be much, much, much larger than the dimension of the code. In fact, we'll show that n is at least something like, so p to the delta d. Okay, so let me first give an example of one error correcting code which has this property. So the code which has this property, suppose this generator matrix G, suppose these V1, V2 up to Vn were in fact all possible vectors of length d. Okay, so if you have putting n equal to p to the d, if you write every possible d-dimensional vector, then these vectors form a vector space of, or the full vector space of dimension d, then you clearly have this property that every vector is in the linear span of many, many pairs. Because you can take the entire subspace and just break it up into pairs. You can almost get a bijection from for every, so you do get a lot of pairs. So for every vector Vj, you will find, for every Vj you will find some Vk, so that Vi is in the span of Vj and Vk. So that's one example.
You don't want to divide, you don't care, because you could say vector of p, right? But you don't.
I don't care about that. So that is one example of such a vector space, and this result is sort of saying that basically that's the only example. There are no other examples. This is the only, basically the only example. So So before I get into this, let me talk. So there's a slightly related notion of locally decodable codes, which is also a very studied notion. So, and this is a weaker notion, decodable. This is a slightly weaker notion than locally decodable codes. So here in locally decodable codes, you don't ask that every coordinate of the original code word is recoverable by making 2 queries into a corrupted code word. You just ask that every message symbol. So suppose C was M times G and M is M1 up to MD. You only ask that every message symbol is recoverable by 2 queries into a corrupted code word. So you're just asking for recovering D coordinates instead of asking to recover all possible N coordinates. So you're asking for much, much less, and this is a strictly weaker condition. So it's easy to see that every locally correctable code is also a locally decodable code. And locally decodable codes have also been intensely studied. And in the 2 query regime, we understand locally decodable codes fully. So we basically know that for all fields F, so a 2 query LDC must have, so the length of the code N must be at least 2 to the omega delta D, exactly this bound, with P replaced by 2. And we know that there exist codes of length 2 to the delta D. And so this is tight. So this was proved by, I think, Goldreich, Karloff, Schulman, and Trevisan first for F2, and then Dvir and Shpilka extended this to all fields. So 2 query LDCs, we understand for all fields it should be 2 to the n. And for a long time, most lower bounds and locally correctable codes followed from lower bounds on locally decodable codes. Since 2 query locally decodable codes needed to have length at least exponential in the dimension, even since LDCs needed to have this, we knew for a long time the LCCs also need to have length at least 2 to the dimension. But on the other hand, the upper bounds didn't match. So though you can have codes of length 2 to the D over all fields for LDCs, this is not true for locally correctable codes. Because again, P to the D was the best example we basically know for locally correctable codes over other finite fields. So for 2 query locally decodable codes, so what is the tight example? Why can you have a code of length 2 to the D which works for all fields? You can just look at basically this set 0, 1 to the D sitting inside FP to the D. This is for LDCs. Okay, so this is the set of size 2 to the D. Look at this entire this set of size 2 to the D. Make these the columns of your matrix, and this is clearly not a locally correctable code. If P is bigger than 2, it's easy to see that this is not a locally correctable code. Every vector here is most likely not in the span of 2 other vectors from here. But it's going to be a locally decodable code because to get local decoding, you only need that the vector is EI, where EI is only 1 in the ith location and 0 is everywhere else. All these EIs should be recoverable by many, many copies from here. So this is a locally decodable code. This is size 2 to the D, and this sits in every field, but this is not a locally correctable code. So this is a non-trivial locally decodable code sitting inside even growing fields.
So what if we have a subfield, or you want to assume that P is prime, not the prime power always?
Let me assume P is prime.
Because otherwise the result is, because you could have a subfield, in the subfield.
So let me say this.
It will not be locally correctable if you use a subfield and you take.
So yeah, so let's do P is prime for all. Setting when it's a subfield, you can the subfield the whole subfield will be a locally correctable code. That's right.
Right. So characteristic 2 you can always do.
Characteristic 2 you can always do, right? That's right.
So P is prime.
Let's say P is prime. Good point.
And also, so you said
there's a construction of size 2 to the delta d. I think you take subspaces of size. I think you take subspaces of dimension delta d and take 1 over delta many disjoint copies of. So if you have a subspace of size 2 to the delta d, so if I look at 0, 1 to the delta d and pad it with zeros maybe. So then that's going to be a locally correctable code which would also correct from delta fraction errors, and you can just take lots of individual copies, and so that this delta is tight. You can get constructions. Okay, so it is for finite fields. So the upper bounds look like p to the d. The lower bounds were 2 to the d. So we didn't know what the right answer was. And so very recently there was a very beautiful work by Boaz, Zev, Avi, and Amir Ehudeyov, who looked at 2-query LCCs over the real numbers of the complexes. So again, for locally decodable codes, we know that they do exist 2-query locally decodable codes over the reals of size 2 to the d, but there is no obvious analog for locally correctable codes over the reals, because the example of taking an entire subspace and hoping that works doesn't work anymore here. And so this paper actually showed that over the reals of complexes, these codes don't exist at all. So you cannot have codes with growing dimension sitting in here. So they basically showed that so the dimension of any such code must be at most something like order 1 over delta to the 9. So if you want to recover from some small constant fraction of errors, then the dimension of the code has to be some fixed constant. You cannot get a growing family of codes.
What is the number above delta?
9. Yes, so some constant depending on delta. So this may not be tight, but that's just a fixed constant. There is no growing family. So this is a very interesting work, and it uses the properties of the reals and complexes crucially. So there is some arguments using matrix scaling which play an important role, and this seems to suggest already that over primes also there must be no non-trivial constructions, but these techniques don't carry over there at all, because these were very specific to characteristic 0. What else did I want to say about this?
You can infer by general principles that there is no.
So this result will, say if this is true over the complexes, then you can, for fp where p is huge, p is like double exponential in n maybe, then you can actually show that they don't exist even over such fields. So when p maybe, I don't know, I think something like 2 to the 2 to the n, then, so again, no 2-query LCCs over fp. And, pardon?
So you can say it the other way around, you get like a minimum, for each prime you get
so this is
delta, you correct? Or
Yeah, you can get, but it's not an interesting bound.
good. So here the primes will be much larger than n. The bound we'll try to get is like you first pick the prime and then let n be huge, or let the dimension be huge, and then can you get a bound. So these only work when the prime is chosen after n is chosen, the length of the code is chosen. And in this setting, when the p is much huger, then there are no locally correctable codes. But because here the example of having the entire subspace of all of p to the d, n being p to the d doesn't work, because p had to be much bigger than n.
So can your result recover this?
Pardon?
So can your result recover this?
It cannot recover this. So let me formally state the theorem now, what we're going to show. Okay, so let me first very formally define what a two-query LCC over FP is once again, and then I'll give a precise theorem statement. So definition. So I say that V equal to V1. So I have a list of vectors sitting inside Fp to the d to the n. I say this is a two-query LCC, or maybe not a two-query, a two-delta LCC.
You mean this is an element, or?
Sorry. Yes, so it's a list. Sorry.
Make sure we are on the
Yeah,
same.
yeah. So it's a. So these correspond to again the columns of the matrix I have there. So it's a two delta LCC. If for all Vi in V and for all sets S of V where size of S is delta n, there exists at least some way of recovering Vi even after you corrupt the elements of V of S. So there exists some Vj and Vk which sit in V minus S such that Vi is in this span of Vj and Vk. So that's my definition. So it's a set of vectors. That's it. Yeah.
So this is much weaker than the
But it's not up to constant factors weaker. If I could replace the delta by delta over 2, it would be the same. Because, but let me just use this version that whenever I have a list of vectors which correspond to the columns of the generator matrix, and whenever I corrupt a set of delta n coordinates, each vector is still in the span of two other vectors which were not sitting in this corrupted set.
You would presume the VIs are distinct now, or not?
So good. So at least in the definition as we have it here, there could be repetitions in the VIs. So that hence I made it a list and not a set. So there could be VIs which are repeated multiple times, and this gives us a lot of problems. So what I'm going to present today is going to be assuming the VIs are distinct. And also if V2 is say thrice V1, then V2 is basically the same as V1 because one is just a scaling of the other. So I'll assume they're distinct and one is not a scaling of the other. So there are no coordinates which are just repeats of other coordinates. Let me just assume that all coordinates are distinct. If I get time, I'll try to say a few words on how we handle multiplicities. So the fact that the VIs need not be distinct and they could occur with varying multiplicities, this also troubled the authors of this paper a lot and gave us also a lot of trouble, but the way we had to resolve it was very different in many ways from the way these people resolved it. And this problem has troubled many other papers also in the past which have tried to prove lower bounds and locally testable codes. So I know Shahar and Vidad, they all were also dealing with some issue with multiplicities, and also Eli and as a student also there was a paper and even they got stuck, and once these VIs could be have different multiplicities of occurring, they just create a lot of problem, and each paper deals with it in their own special way. It could be possible that to have constant query decoding or correcting or testing, multiplicities don't help. It would be very nice to have a result of the form that whenever there is a locally correctable code which with elements appearing with multiplicities, you can toss away the things and get an equivalent code without these multiplicities, and that would be very, very useful. But the fact that they can occur with varying multiplicities creates a lot of trouble. But so
in
then
all cases, the results say that up to constants is the same. After all this trouble, you go to what you realize that they don't seem to help.
You
But
lose
we
the
don't have-
estimate.
Yeah, so you lose some. Yeah, that's right. Maybe a power of delta is different, or it's not clear why there's no black box reduction. Of course, with multiple without multiplicity, but we don't.
So we deal with this, but for now, let me just assume they're all distinct, and there are no two which are multiples of each other. So every two Vi Vj's, they are linearly independent. Yes. And so for now, So for all ij, you have vi does not belong to the span of vj.
Of course, the simplest codes of all, which is just send the message twice.
And for
Yes.
data, which is very,
Yeah, but
very
you
small.
don't get, so you can,
For
you,
data,
you,
which
no,
is-
but you see, if you want the dimensions to be.
Oh, no,
Yeah,
I
but
see,
for
but
data
what
very
I
small,
mean is
that's
that
it,
it's,
right.
Yeah, for
So
data
we
very
need to
small,
say
that's
for
fine.
data very
Yeah.
small,
No, for this,
repetitions
yeah,
too,
yeah.
and therefore.
Yeah, that's what. Yeah, so just send the message twice is a redundant code
That
yeah,
people have used.
I've used this
For
in the
ages.
past.
Okay. So let's assume this and okay, good. Okay, so the main theorem now. So this is the main result. So let again. So suppose v, which is v1 to vn. So this is a 2-query LCC. Then we show that the dimension of v. So we look at these vectors. Look at this. Look at the dimension of the vector space they span. We show that this is smaller than order 1 over delta times log n to the base p plus some polynomial depending on p and 1 over delta. This order can actually be made something like 2 plus epsilon over delta for some small constant epsilon. So if this constant was not there, this is basically as tight as you can hope. Once p starts getting compared, once p starts getting something like log n, then this quantity will take over and this will become smaller, and then the bounds are not that great. So when n is much bigger than p, then this term dominates and then the result is sort of tight. So you take any large prime p, take n to be much larger than p, and then ask for a locally correctable code in n coordinates and the dimension, then such a code must basically look like a subspace. So hence this result doesn't recover this in particular, and says nothing about the reals or complexes, anything, because once p gets, if this term was not there and this was true for all primes p, then by some compactness argument it would be maybe true over the complexes too, and etc. But for when p is large, then this is giving nothing. Okay.
And if you don't have repetitions, you still get this term?
Yeah. So with repetitions, without repetitions, everything, the bound is the same. The constants in the polynomial might change a bit.
Everything is worse when you have repetition.
Oh yeah, but okay, I don't know that. To make sure this term doesn't come because of handling repetitions.
Yeah. So it'd be very interesting to get rid of this. It's conceivable that it need not exist, but in our proof, it is we heavily use that extra term. And then when I talk about the proof, you'll see why it's not going to work for large p at all. It's only going to work for when p is much smaller than n log n.
When p is 1 over delta, if you have repetition, you just send the same symbol p times. It's just a repetition code. Then you have to have something of this. But
No, this is about delta, not about
delta. No, but it's together.
But p, this is about the relation. She's talking about the relation between p and n, and not delta.
Yes, for any, I'm taking n to be p to be 1 over delta.
Right. Yeah. So if also
N equals p over 1 over delta.
then you should do something.
Something.
Okay. Okay. So I'll get into the proof of this result. So other than this work, which showed non-existence of LCCs over reals, all other lower bounds for LCCs that we know today, I think, follow from lower bounds for locally decodable codes. So none of the proofs could really exploit the local correction property. They only use a local decoding property. So we need to start somewhere else. We need to somehow use the fact that it is a locally correctable code, because we want to show separation between LDCs and LCCs over these finite fields. So we'll need a different proof which will use a local correction. So let me first just recover the old bound of 2 to the n, 2 to the d, but now critically using this local correction property. And then this is a proof, though it's going to start with a stronger hypothesis and recover an old bound. This is the proof which will generalize more generally for to larger primes and deal with repetitions, etc. So let me first prove this result over F2. So over F2, anyways, we know type bounds, but I'll give you a new proof. Okay, so we'll do a new proof over F2. And this is going to use local correction, and the main tools we're going to use are tools from additive combinatorics. So in particular, the Balog-Zemeredi-Gowers theorem and the Ruja theorem. So these will come together, and we'll give a new proof of the 2 to the delta d lower bound over F2, and then I will talk about how to extend these to primes. So let me just let me state these theorems which I'll be using, the Balog-Zemeredi-Gowers and the Ruja, the versions of the theorems. I'll state them accurately and then get into the proof of this result. So let me do Balog-Zemeredi-Gowers over Fp. So so the statement is the following. So let epsilon greater than 0 be any small constant, and say A and B are subsets of Fp to the d. Suppose there is epsilon A square such that, okay, suppose there is epsilon times size of A square number of pairs Ai and Aj, such that Ai plus Aj belongs to the set B. So I have two sets A and B in Fp to the d, and for epsilon fraction of the pairs sitting in A cross A, the sum of the pairs lies in B. Then there exists a subset A prime of A, where A prime is where the size of A prime is pretty big. It is at least epsilon over 2 times the size of A. So there's a pretty big subset of A, which doesn't expand much when you take the sum of itself with itself. So such that if you look at A prime minus A prime, and look at this different set. So you look at the difference of all pairs of elements in A prime, then this thing doesn't grow by too much. So I think the best is something like 4 over epsilon, some constant depending to the 4 over epsilon to the 8 times size of B to the 4. So I think we'll typically be using A equal to B. So basically if you have a set where you have lots of pairs of elements whose sum stays in the set, then there's a subset of cardinality at least epsilon times A, where A minus A is at most some constant depending on epsilon times the size of A. So it doesn't grow much at all. Okay, so this is the form we'll be using it in. So the dependence on P didn't show up. It doesn't matter if you were for this theorem if you were working over F2 or Fp. I mean, these constants behave nicely. Let me mention the other result I'll be using, which is the result by Ruja, which says that, now suppose you have A, which is subset of Fp to the D, and you have the property that A minus A, this is not too big, this is less than k times size of A. So the difference set doesn't grow too much, the growing factor is just some k. Then we show that A in fact must be very, very close to a subspace. So then the dimension of A, where the dimension of A is, look at all the elements of A and look at the vector space they span, look at the dimension of that. So show that then the dimension of A is actually at most log of the size of A to the base P plus something like 2 times k to the 4. Another, so what we're saying was if A minus A, so maybe the more standard way of seeing this was if A minus A is at most k times A, then the size of the span of A, this is at most k square times p to the k to the 4 times A.
And this k to the 4 can be improved, right? So given out something that gets almost tight bounds there. So
Yeah.
What do they get?
Constant. No, so they have a better. So here it's k to some power below 4, and they have k multiplied by the right constant plus some little order of k term.
So which result is this?
Even in TAF, maybe 2 years ago.
Okay. No, they won't affect anything in what we're doing, because these polynomials here are going to get so bad that it's not going to matter. Okay, so basically if A minus A doesn't grow much, then the span of A in fact is not much larger than A. And here this constant P is going to show up, because if you're working over Fp, then when you take the span of A, how much it grows by is going to depend heavily on this quantity P. So when P is very, very big, then even if A plus A doesn't grow too much, the span of A could grow by a lot, just because P is big. So that's one place where we're going to only not be able to deal with huge quantities of P, because we're going to be using this result, and that's already sort of limiting.
So what you wrote there is if the dimension is plus 2 plus k to the 4 and not plus 2 k to the 4.
Yeah, so this is a bound, right, exactly. But I was just making it one polynomial. Yeah, so some polynomial depending on k was what was important. Okay, so this is basically one of the main reasons why we're going to you only deal with small p. Okay, so now these results already look like they're perfect for using in the setting we're in, because suppose you want to prove this result over F2. So what does it mean that Vi is in the span of Vj and Vk? It means that basically over F2 it means that Vi is equal to Vj plus Vk. So there are going to be lots of pairs Vj, Vk whose sum is Vi, so whose sum stays within this original set. So basically, so now an LCC over F2 immediately gives a set which has a lot of additive pairs in it, and now you can immediately apply BSG and Ruja and then see what you get. So shall I prove? So let me give a new proof over F2. Okay, good. So here is the proof. So let's so you have V, which is a set now, because we go all distinct, V1 up to Vn, sitting in Fp to the D, and this is and save now the F2 to the D, and this is a this is an LCC of this form. So if you have a two query, if you have a 2 delta LCC means how there must be at least delta fraction of pairs, that is delta n pairs which add up to Vi for every I. So for all Vi, there exists at least delta n pairs Vj Vk belonging to V square such that Vj plus Vk equals to Vi. So the LCC property just immediately gives this. And now if you run over all choices of I, so you will get this, so implies so there are at least delta n square pairs in particular, Vi prime sitting in V, who's such that the sum also sits in V.
What's special about F2 in this case is that there are no coefficients.
There are no coefficients, exactly. So why is F2 much simpler here? Because if we were working over Fp, then we would get that that Vi was in the span of Vj and Vk. So there's some alpha Vj plus gamma Vk would be Vi. And in this statement we don't really know how to apply BSG and Ruja there, because that result is not talking about linear combinations, it's only talking about sums. You need sum sets, not different scalings of sets. So over F2 things are much simpler, we can apply these results directly.
So how are you using the fact that Vj, Vk are distinct?
I don't care that Vj and Vk are distinct. So I think if you want Vj and all these pairs to be distinct, you would only get delta n over 2 pairs.
I mean disjoint, not distinct, but
They're not. I'm not using the disjoint.
but disjointness is crucial for these definitions of LCC.
Well, it's automatic in this case. I mean, Vi could not be the sum of non-disjoint pairs.
True, you're right. Yeah.
So, at that moment, it's okay.
Okay. Yes. So they couldn't be disjoint, but okay. So but you at least have so many pairs. LCC, whatever. So all that I'm using is there are lots of pairs which sum to it. Maybe we'll be using the disjointness in the proof later. Actually, this is not going to be it yet. Okay, so there are delta n square pairs sitting in V, whose sum is also in V. Now you can immediately apply the BSG theorem. So BSG will imply. So there exists this set of V prime sitting in V, where the size of V prime is at least delta over 2 times n, and V prime minus V prime is small. This is whatever it is. It's going to be, yes, 4 over 8 to the delta times.
The other way around. 4 over delta to the 8.
4 over delta to the 8 times size of V. Okay? And so you get this. So V minus V prime doesn't grow much, and in fact, hence the dimension of V prime is going to be small. So now Ruja will imply that dimension of V prime is at most log n to the base p plus some polynomial in 1 over delta.
So P is 2, right?
And so this is pretty close to what we wanted. What we want to show is the dimension. So we got that there's a pretty large subset of V which has small dimensions. We wanted to show that all of V in fact has low dimension. So we are not done yet. We just showed that there's a large subset of V which has small dimension. So the way we're going to do it now is, we got a pretty large subset which has small dimension. So intuitively what we're going to do is we're going to strip off this subset, look at the remainder and hope that it is still, the remainder looks like an LCC, and we can apply BSG and Ruja once again on it, remove a small or large subset of that which has low dimension, and keep doing this iteratively till we can show that the entire set in fact has low dimension. So here we got a set, here we got a set of size delta over 2 times n which had small dimension. So we can hopefully we can keep peeling off sets of size delta over 2 times n. This process will happen at most 2 over delta times, and the resulting dimension will be 2 over delta times log n, because we just each new LCC we find will increase the dimension by log n. Okay, so in the just nutshell, that's the proof, but you need to be a little bit careful. So okay, so let me fully do it formally. So I want to show that we got a big set which has small dimension. We want to amplify the size of the set. Okay, so let me write this amplification lemma. Okay, so here's the lemma. So suppose you have any set S of V. So suppose S is any set, and this set is closed under taking span inside V. Okay, so if you look at the span of S, and if there are any other vectors, elements in V which lie in S, we'll add it to S. So say S is any set, and the span in V of S is S itself. Okay, so suppose you have this property, then we'll show that we can grow S to a bigger set, to a much bigger set, and the dimension of the new set is not much larger than the dimension of S. So let me show there exists a set S prime which contains S, and so contained in V. Again, let's assume that span in V of S prime is S prime. So there's any more things in the span, just toss it into S prime. Then, so either we can get, now I want to show that S prime is much bigger than S. So either size of S prime is already n, or the size of S prime is much bigger than S, it is S plus maybe delta over 6 times n. Okay, so I want to create a bigger set whose size is much bigger than the size of S, and the dimension of S prime, it doesn't grow by much. So it contains S already, so it's at least dimension of S plus log n to the base 2 plus some polynomial in 1 over delta. Okay. Suppose I can show this amplification lemma, then this will imply the full result, because then I can iteratively find one LCC, I can find one large subset which has low dimension, and then apply, and let that be the set S, and I can keep growing it, and each time I grow it, I'll include a lot more elements, but the dimension won't increase by much. And so I can just apply this lemma 2 over delta times, and I'll get that the entire set S must in fact be of low dimension.
So you assume here also that V is
V is subspace. The amplification, V was a 2 in the same setting. V was a 2 delta LCC over F2.
The amplification lemma has a special case what you showed us for S equal M.
Exactly. When S was the empty set, I just showed you what the that was the proof of the amplification lemma.
What was this 2 over delta? So you iterated 6 over delta?
6 over delta, sorry. So the growth is here just 6 over delta. So I'll have to repeat the 6 over delta times. Okay.
So the dimension will grow to 6 over delta times log V.
Yeah, log n.
Log N.
Yeah. And that will be, so and hence we'll get a lower bound of, so I've not shown this, I'm not making it tight up to the factor 2, but it will be some constant over delta times log n. Okay. So when S is not the empty set, when S is some set, whatever is outside S need not be in LCC, because you might be able to decode things from outside S using elements from S. So that's the thing we need to deal with. So I don't know how would you do, but why should the rest be an LCC?
Because now, so you can project it to 0, but then every time you want to read a bit from S, it's 0. So you don't have to read it. So you get either element repetition or
But then, even if you had no multiplicities before, you couldn't reproduce.
yeah, that's true. Now you can understand.
Okay, good point. Okay, I didn't know what to say. Okay, but the proof is not much harder than that. So you have your set S. So you start with your set S. Now you know that for all vectors Vi, which are in V minus S, this is for all vectors Vi, but in particular for vectors in V minus S, you are able to decode Vi from lots of pairs. And in fact, you'll be able to decode all these VIs from lots of disjoint pairs. So there'll be, so in particular there exists, let me call this a matching. So I say Mi is a matching to decode I. There are lots of disjoint pairs of coordinates whose sum adds up to Vi. So there's a matching Mi, which is in V cross V of size delta n over 2. Right? So there is a matching which will decode, which corresponds to Vi. Now, if most of these pairs in the matching are already sitting inside V minus S, then it's great because V minus S looks like an LCC for decoding Vi. But if a lot of these pairs are getting help from the set S, then it's not an LCC anymore.
So now you're going to use the B different than A in the parallel.
Maybe that's also another way of doing it, but here's a much more first principles way of doing it. So degree is matching. So suppose there, I don't know, so delta over 100, so suppose there's a tiny fraction of this matching, even if a tiny fraction of this matching intersects the set S, suppose, let me call it edges of the matching, suppose a tiny fraction of the edges intersects, each intersect S. Suppose at least this tiny fraction intersects the set S, then I'll add this vector Vi to S. So I don't like Vi being in outside S. Let's see what happens when I put Vi into the set S. So what's going to happen when I add Vi to the set S? Since
you're going to decrease V because you're going to increase the dimension by 1, but you're going to decrease the size of V minus S by that constant amount.
Exactly. So what happens is since S was closed undertaking span, what happens is if there's an edge Vj Vk which adds up to Vi, both Vj and Vk cannot be part of S because then Vi would have also been part of S. Right? So every edge of the matching will intersect S in at most 1 coordinate or 0 coordinates. Suppose there are lots of edges which intersect S in 1 coordinate. If I throw in Vi into S, then the other coordinate of those edges will also fall into S. So I'll add Vi to S and take closure under span and just take the span. Okay, so by this step I will increase the dimension by 1, but I'll increase the size of S by a linear factor. Okay, so I'll keep repeatedly doing that. I'll find the sum Vi whose matching intersects S too often, I'll throw Vi into S, and I'll keep doing this till I can't do it anymore. So keep doing till can't anymore. Okay, so and then call this new set maybe S star after you keep throwing in whatever elements you could and taking the closure under span. So what will happen is that the dimension of S star will not have grown by too much. So the dimension of S star will grow by at most 100 over delta to the 100, just by some constant depending on delta. Right? Because this process of throwing in can happen at most a constant number of times, and each time you increase the dimension by at most 1. So S star will have basically roughly the same dimension, and okay, good. And then the size is increased by some, but increasing of size is only good. Okay, now two things might happen. Either S star is already the full set, is all of V. What happens in that case? I'll call my S prime to be the set S star, and S prime will have all the properties. Okay? Otherwise, S star is not the full set. So if S star is V, then you're done. We met all the conditions of the claim. Else, look at V. Look at the set V minus S star. Now this is a pretty good LCC. What happens in V minus S star? Every element in V minus S star has a matching of size at least delta over 2n minus this quantity, which sits, then this matching sits fully inside V minus S star. So else V minus S star is a good LCC. Yeah, and then what does it mean? So for all Vi in V minus S star, there exists this matching Mi of size at least, originally the matching had size delta over 2 times n, and now you might have lost at most.
Why is it so simple? I mean, why didn't you choose like delta over 100?
I could have. So I could have chosen this to be just delta square or delta something much smaller, but when I'm trying to understand the paper, just to show that delta over 100 is much smaller than delta, I mean the 100 helps in thinking that this is a small quantity which cannot affect anything. This could have been much simpler, but
So will not come some future reason why.
it is not good. The 100 is not good. This 100 could have been a 2. Delta square. You need
1 over delta times.
right. You need delta square maybe. So there is the matching of size at least this in V minus S star square. Okay, so hence it is a pretty good LCC. Now we can apply again BSG and Ruja to this setting. And then it's not hard to see that when you apply it exactly to the setting, what you will get, you will be able to extract a pretty large subset of V minus S star, which has small dimension. And the yeah, that's it.
Sorry, keep on going. I thought you were, when you're at a breaking point, I have a comment.
Okay. You can write on this board or doesn't matter. Yeah. Okay. So that's basically it. So now, when you apply BST and Ruja, what do you get? So you have a matching of size at least delta over 2n minus delta. So this quantity. So in particular, V minus S star is 2 minus. So it's at least a 2 and this LCC, but in fact it's even better. It's 2 times this. So the total number of matchings is this times n, but the size of V minus S star might be much smaller. So the density of matchings might be higher. So it is this times n over V minus S star. So this is this LCC. This is sort of important. Just otherwise, some delta will become a delta square somewhere out there. If what I care about this, right, that exponent delta will become a delta square. So because V minus has an LCC of this size, So now, so hence now there exists a set S prime, which is subset of V. So now let's apply BSG, and the size of S prime is going to be, if it was a delta LCC, the size was going to be delta over 2 times the size of the set. So now it was this LCC, it will be this over 2 times V minus S star. So it's going to be half of delta over 2 minus delta to the times V minus S star, and this is at least, so V minus S star cancels, this is at least delta over 3, so this is at least delta over 6 times n. If I hadn't put in the V minus S, n over V minus S star, I would have gotten a worse bound there. So the size of S star is at least delta over 6 times n, and by Ruja, and you have that the dimension of S star is small, log n plus poly 1 over delta.
I mean, it's okay, but without this, I mean, you know that you don't have to worry when V minus S star becomes very small, smaller than delta over 6n or something.
Right.
Then you don't have to worry because anyway many of the matchings.
Right, right, right.
Yes, so V minus S star is big, and
Right.
therefore even. But anyway,
Right, right, right. And that point's actually going to come up in a very, that observation is going to be very, very important very soon, somehow, but in the talk. But doesn't matter right now. Okay, so you do get a large set with small dimension, and hence you can amplify the set, and you can keep amplifying it by this process till you reach everything, and this is the full proof of the exponential lower bound over F2. Yeah.
Okay, so now you're at a stopping point. So I think you don't, you could replace combining BSG with Rusha in this argument with a different result from additive combinatorics, which says basically so the condition that you're stating, the hypothesis for the BSG is essentially that the collision probability of the distribution A minus A is relatively large. So the B over A is is how much it's okay. So it's basically 1 over B times epsilon. So under that condition that the collision probability of a set of the difference of the set is a much bigger than 1 in the size of the set, you can prove directly that there is a large that there's a subspace of about the same size as the set with a constant fraction intersection with the set. So you get a subspace whose dimension is about the size of the set. So its dimension is going to be this log base p of n. Or okay, I'm not quite sure whether this is true over. I've seen it over characteristic 2 should generalize to b, but I'm not sure how it does quantitatively. So the dimension is right, and it's going to have a big intersection with b.
That's what she's using.
So
That's what you're using. So you don't have to have it actually contained. It's not actually contained in b, but it has a big chunk of b is in this relatively small subspace, which is all you actually need.
Which is also what you're sort of concluding from here, that there.
That's right. So saying the chaining the two together.
Yeah.
There's actually like you have like 2 arrows. There's basically another result that just gives a direct arrow with different quantitative bounds.
Is this the Freiman-Ruja theorem?
And I don't know who
I'm not
this
sure.
is. So I was looking at it about 8 years ago, but other people looked at it before me, and recently, I think. So Ryan was telling me that there's a recent, about a recent improvement. It might have been Bolos that did it. So, so you might want to talk to him about the most recent status.
Okay.
Avi,
No, I think it's essentially the same. I know
if you remember whose theorem it is.
The polynomial Feynman-Wooster conjecture, which was improved, but it doesn't affect. What?
For the parameters, it doesn't matter.
Yeah, exactly. It doesn't affect much.
Okay, so that's the full proof over F2. So what are the issues which now, so let's try to extend this to FP. Okay, so what are the issues that come up? So one issue is, so let's try to just repeat this over FP. What's going to break down is we don't know how to even start using BSG and Ruja because the decoding might happen by linear combinations and not by sums.
Yeah, but if you think of P as small and N as large, you can just take all multiples of your vectors.
Which is what we do. So that's an easy fix to that. What you can do is you just take your vectors and take all possible multiples of the vectors. So you blow up your set by a factor of P. But now the decoding can happen by sums. So you get a slightly weaker LCC, but now you can apply BSG and Ruja. Okay, good. So that's so that step is not hard. So I'm not going to talk about multiplicities as yet at all, but so let's do that, and now let's apply BSG and Ruja, and we're going to get stuck in one important point. So the point we're going to get stuck at is you get a weaker LCC. If you had a delta LCC before, you get a delta over P LCC. Okay, so by blowing everything up by a factor of P. So if you have a delta over P LCC, what's going to happen is wherever you see deltas here, now you will replace them with delta over P. Okay, so in particular, you'll have to repeat this amplification lemma. Instead of 1 over delta times, you'll have to repeat it P over delta times. If you're going to repeat the amplification lemma P over delta times, what's going to happen is the new set, you will have dimension P over delta times log n. But P over delta times log n is too weak.
But it already decomposes, right? I mean, when you multiply it, take P copies of your original set, and now you use the LCC property. So the coefficients will be replaced by, I mean, it seems like the matchings will decompose into P different matchings, and you might have to run them in parallel. I mean, I don't know.
But it's still for each separate, you may be able to decompose the LCC, but it's still a.
But you'll get from each one a function of delta over P times.
Yeah, you'll not get a factor of P because of all the matrices.
But you won't be able to decompose. I don't think you're going to take the whole set and be able to break it up into P different parts because the decomposition is going to happen. So suppose there's a VI, VJ, VK where VI is in the span of VJ and VK.
No, I understand,
right.
But when you do this argument,
right.
Like when you look at the pairs which have delta
right.
squared over 100,
right.
so
right.
there'll be
right.
P such chunks with this fraction.
Right.
So that kind of thing you.
So we're going to do something, but it's somehow very, very so maybe there's an easier way of doing it, and that would be great. So, but so we have a much more not much more complicated, but it does get trickier. So let's do the proof over FP. So and exactly by that outline. So you have the set V. So let's replace V by the set V tilde, which is C times Vi. So you take all scalar multiples of elements in V and add it to V tilde, where Vi is in V and C is in, that would be FP star.
Yeah, this of course doesn't satisfy your non-redundancy condition.
Doesn't satisfy my non-redundancy question, but we probably never needed that the multiples were not there maybe till now. So now, but we were, I think, but we were using the fact that there are no multiplicities in all this. There are no repeats, because
At some point use the fact that it's a prime field, right? I don't see where it will come. Because we said that the result is false for a
Also,
non-prime field.
BSG and BSG
Oh,
and
maybe
Grusha are
Maybe.
also,
Grusha is not there.
yeah.
this version I'm using, I think, is for.
So this is just for prime because
I'm not fully sure though. Is that true? Good. Okay, so we get this set V tilde.
FP star is just non-zero.
FP star is all the non-zero elements in FP. So you've blown up every element. Now you have to have all scalar multiples, and now let's look at. So now originally when you were recovering using linear combinations, now you'll be able to recover using additions, because when Vi was getting recovered with by alpha Vj plus beta Vk. Now we'll just but alpha Vj is in the set and beta Vk is in the set. So now the decomposition is going to happen by additions. So let's look at, let's ask that we only recover using additions, and so this is still going to be an LCC, but it's going to be an LCC which is going to be slightly weaker. So now for all Vi tilde in V tilde, there are, so originally you had delta n pairs whose linear combinations added up to Vi. Now you'll have the delta n pairs in V tilde square whose sum adds up to Vi. So it will be such pairs Vj tilde Vk tilde such that Vj tilde. Okay, so there will be delta n so many pairs whose sum adds up to Vi. Okay, so let's say, so in particular V tilde will have lot of additive pairs, a lot of pairs whose sum stays within Vi. So there are at least, and you can do this for each Vi tilde, so there are at least n times p minus 1 times delta n pairs whose sum is in P, stays in V tilde. Okay, so and this quantity is what fraction of n times P minus, this is delta over P minus 1 frac times n P minus 1, which is the size of V tilde square. So a delta over P minus 1 fraction of all the pairs has such that the sum stays in V tilde. And now we can again apply, in the setting where we can apply BSG and Roja and see what we get. Let me leave that up. Okay, so this is exactly the same setting. So now BSG will give that there exists B tilde prime sitting inside V tilde, where size of V tilde prime is now delta over 2p minus 1 times size of n times p minus 1. Yeah. And dimension of v tilde prime. This is again still small. It's going to be log of np plus something. So this is going to be again log n to the base p now plus some polynomial which depends on p and 1 over delta. Okay, so you directly apply bs, so this is bsg plus Ruja. So now, so let's so now we could similarly have an amplification lemma of that form. So now, so here you got a pretty big subset which was delta over 2p minus 1 fraction whose dimension is small. So what we would hope would be to just apply that amplification lemma in a similar spirit to what we did last time. And so you get one large subset with small dimensions, strip it off, hope that the result is still a good LCC, and then keep repeating the BSG Ruja kind of steps and till you cover the entire set. But what will happen is if you do it the way we did it before, this will repeat this step. This will get repeated at least 2p over delta times. So the amplification lemma, if you just use it as before, what we'll get is eventually we'll get that the dimension of all of v tilde is going to be at most 2p minus 1 over delta.
Can you project v tilde prime back down to v prime to v?
Okay.
Because each element of v tilde prime is some multiple of
Right.
some element of v
Right.
prime.
Right.
So question is how many of
So the dimension may not change, right? So even if I project it down, the dimension won't change, and the size will also not. Oh, the hope is that now the
the
right.
size would be still delta n rather than
Right.
delta n over p. So
if the size was
yeah,
maybe you don't get the best you'll hope you'll still get delta over p times n. I don't think you'll be able to argue.
I mean, the set v prime, which is a prime, is closed as a subspace within v.
Right.
So it contains all the multiples.
Okay.
So it has to lose like.
You don't gain and you don't lose.
Yeah.
It will be exactly the same.
No, but then the fraction has to be.
It's a factor of p in the. So if you project, you lose the factor of p in the size of v prime, and you lose the factor of p in the total size.
Mhm.
It's the same. So this will not.
So we just go. So I don't see any simple this just scaling down will not give it because the dimension will stay the same, but the size of v prime doesn't seem to go all the way. And so now if you repeat the amplification lemma, this is not a good enough. This is a very, very weak bound. You're getting dimension at most p times log p to the n is weaker than the earlier bound we got with log n to the base 2. So we wanted to improve log n to the base 2 by log n to the base p, and this factor is too much. So we can't imply the amplification lemma as is. If we could get rid of this factor p minus 1 out here, then we would be done. Then we can imply the amplification lemma. Okay, so what I'm going to show you is how to get this same statement without this factor of p minus 1. And the proof of this result, which is going to get rid of this factor p minus 1, is going to sound a lot like this amplification lemma statement, but it's in a very different spirit somehow. We are not going to create any sets. It's sort of going to happen more in the head as a thought process. Let me is a bad. So the lemma is, so I'll get the same statement up here without the P. So if V tilde was an LCC, which was did this so actually before I get back, let me just project, let me actually project this down, and just I won't gain anything, but I don't want to deal with the tilde set anymore. Let me just deal with V directly. So so I got this statement. I got a V tilde prime sitting in V prime, which is small dimension. So this implies there exists V tilde sitting in V. If I scale everything down, the size of V tilde is going to be at least delta over 2p minus 1 times n. V prime, sorry.
And that's V tilde up there.
Here. Sorry, good. So there exists V prime. Now I just scale everything down to the original set V. I get a V prime sitting in V. Where V prime is pretty big. It's going to be delta over 2p minus 1 times n. And the dimension of V prime won't be any more than the dimension of V tilde prime. So dimension of V prime is small. So now let's forget this the tildes completely. So if I started with a set which was an LCC, forget that I was doing sums or anything. Now I start with a set which was LCC using linear combinations, and I can deduce that there is a subset of size delta over 2p minus 1 which has small dimension. So this I can always do whenever I have a 2 delta LCC. Now using this, I want to show that in fact if V is a 2 delta LCC, then there exists this set V star where size of V star is in fact, I don't know what bound I get here. Okay, delta over 3 times V. So I'll replace the delta over p minus 1 by delta over 3, and the dimension of V star is at most, again, there's no constant here, just log n to the base p. Polynomial Pn with no delta. So I'll just use that result black box to now prove that you can get, without increasing the dimension at all, maybe you increase something here, but without increasing anything here, you can get a much larger subset. So let me, so the way you're going to do it is, so let's try to apply the amplification lemma to that step. And I'll say that you keep applying the amplification lemma. So each time you apply the amplification lemma, you're going to add on a set of size delta over p minus 1. You're going to keep growing a set by a factor of delta over p minus 1. But I'll show that in fact when you apply the amplification lemma, you can't keep adding on a set of delta over p minus 1. At some stage, you'll actually have thrown in a much larger set, a set which is actually of size something like delta times n. What if I can't?
Maybe you can't apply that. Maybe you can't do. Oh, you're saying not just a part that's at one's element, general.
See, so what you're saying, I think, is you have this B prime, okay? While it's small, think of the elements in B prime as corrupted so they can't be used. And what's left is still, because B prime is small, is still an LCC, and so you get a new B prime. And you just keep on doing that, and so you get this sort of collection of B prime.
At some point, V prime will become big.
And at some point, B prime becomes big.
Yeah.
But why can't this go on many stages with small increments, rather than there being a big jump? Is that what you're going to show?
So I want to show that why can't it go on too long with small increments is what I want to show.
Yeah.
But so it could be that at some point, as you grow it, the set becomes pretty big. But why can't I just keep incrementing it by a small amount? Yeah. Maybe you can just keep incrementing by a small amount all the way, but that can't happen. Okay. So so what we'll do, we'll start with a set. Again, everything which is outside the set, whose matchings intersect the set so far in many points, we'll get rid of all those elements and we'll toss it into the original set. And the rest is going to be a good LCC. And now you'll repeat that lemma to that good LCC, and you want to keep doing it. Okay, so that's the process. We're going to have a set. We'll start with some set S1, where we will extract an LCC. It's going to have some size and pretty small dimension, and then everything which is outside S1, which is decoded by a lot of elements from S1, something like delta over 100 over p to the 100. We'll throw all those guys into S1, and we'll get this augmented S1. And whatever is outside this augmented S1 will be a good LCC. So we'll get a set S2 maybe. And then we'll toss in all the things which take help from S2, and we'll get the set S2 star. And then we'll keep going. And
when you define S2 star, so what if things get a lot of help from some member of S1 star and one member of S2 star?
Good. So I know that whatever is outside S1 star is a good LCC. I'll never care about S1 star ever again. Okay. And all the things outside here, I only see do they get help from here or not. If they get help from here, I'll toss them into S2 star. Otherwise, they better be a good LCC in the remainder, because this was a good LCC. So that's what's going to happen. Once I augment S1 to S1 star, I'll never look at S1 star ever again, and I'll argue with the rest of the set. And so what's going to happen is, originally it was a delta LCC. Originally the entire set was a delta LCC. Then I found S1, I augmented it to S1 star. Then at the next stage, I'll get a delta minus delta to the 100 over p to the 100 LCC at stage 2. Right? Because the quality of the LCC is degraded only by a small amount. Because all the things which got help, at least delta over 100 times p over 100 times, I put them in here. Everything else is basically decoded in this part. So the quality of the LCC is still pretty good. At the next stage, my LCC quality will be delta minus twice delta to the 100 over p to the 100, and so on. Right, so the LCC quality is going to keep being good, and I'll keep doing this process, this amplification lemma, till I run out, till I include all the elements. So this amplification, how many steps can be there in the amplification lemma? Not too many, because each time I'm stripping off a set of size at least delta over p. Okay? So number of steps in the amplification is less than, I don't know, 100 p over delta. Okay, so the number of steps is going to be small, which means, and each time, each step, the quality of my LCC is losing by a little bit. But since the number of steps is small, that means basically my LCC is at least a delta over 2 LCC.
Either it terminates early or you would end up with too high quality.
Exactly. So what's going to happen is, so the number of steps is anyway just 100p over delta. So that means each time the quality of the LCC in the remaining set is, so at each stage, so the LCC, I don't know, quality is at least delta minus delta to the 99 over p to the 99, which is at least delta over 2. Because at each stage at least have a delta over 2 LCC. Good. And now let's see, and we keep stripping off these sets and let's keep doing. Then the claim is that one, okay, so what happens? So you stripped off, so this is S1 star. You got this set S1 star. Then you will get a set S2 star. And you will keep going. And suppose it went on for a number of steps, say k steps. Let's look at what happened to the k minus 1 step. Okay, so you reached and you got sk minus 1 star. So you reach up to sk minus 1 star, and in one more step you're going to finish everything. Okay. So I claim that in the last step must be a big step. Why must it be a big step? In the last step you're going to take all of this, right? But can this be small? Well, it can't be small because this thing is a pretty good LCC. It is a delta over 2 LCC. If this thing is a delta over 2 LCC,
Delta over 2 even with respect to the original n, right?
is that, in fact, oh right, good, sorry. It's delta over 2 LCC with respect to the original n. So the number, you say the LCC quality, this means the number of matchings is at least delta over 2 times n. So in particular, the number of elements out here must be at least delta over 2 times n. And so, that's the full thing. So in this last stage of the step of the amplification process, you must take a huge number of elements.
So yeah, so the last step is big.
So the last step is big. So this last step has a big number of elements and it has small dimension.
Okay, but what about all the previous ones?
So I don't know, all these previous ones might be small sets, small dimension, but this is a big, this one is a big set, small dimension.
Didn't we get an addition of dimension of log base p of n in each of the small sets?
Right, but I won't care about these.
Don't take the union. We don't
I don't take the union. I look at S1 star and I look at the rest. I get a set S2 star. I never take the union. Don't take them. I'm not going to run this process. I'm just doing it in my head.
Just take this one big step. Yeah.
And I realize that at some stage there is a big step, means there exists a big set with small dimension. And that was this lemma.
Sorry. So could you say again why that last step has to be big?
This last step, so what happens is, so this is a delta LCC. It's actually, so this is a delta LCC means there are delta over 2 times n number of disjoint matchings out here.
Yeah.
The number of disjoint matchings in the second step, once I get rid of this, the number of disjoint matchings in this is at least delta over 2 minus this times n. So at each stage, when I say the LCC quality is large, I should actually say that means the number of matchings. At each stage, there are at least delta over 2 times n minus minus delta to the 99 over p to the 99 disjoint matchings. Disjoint edges. So you have at each stage you have at least that many elements left over.
Right. Okay.
And so.
And after the last stage, you have nothing left over?
So what was each stage? Each stage you extracted, so a stage was comprised of 2 substages. One was you got an LCC and you used BSG and Rujo to get a small subset, and then you tossed it, and everything outside which got a lot of help from this set, you tossed it in.
Yeah.
So that was a stage.
Right.
So at the end of it,
What's your termination condition? Just when
all the n elements got used up. So this process ends when all n elements get used up.
Okay. So
Since
that certainly means that the last. And how do we know that we'll be able to keep on going till all the last?
Well, I mean, K.
Oh, because you have this delta over 2 property. So you can keep on going as long as there are any elements left at all. There have to be at least delta over 2 elements.
So for instance, suppose at the end you were left with some and you got an LCC, and it was going to be a small set. But if this set was only anyways delta over n, delta n, and once you got an LCC, everything outside must have got a lot of help from here anyways, and then you would have ended up tossing all these things into it, not growing the dimension by much, and having a big set. This was exactly the remark. Yeah, this is what you said. So so this was the crucial point that, right? The reason, yeah, good.
The nice thing is that you have all these steps, but actually you are using only the last one.
So this is just to show that there exists a big set with small dimension, and once you have that big set with small dimension, now you can use the usual amplification lemma, where you actually take these sets and the next set and the next set.
And when you say that small dimension,
So
okay.
each set in this step has dimension 1 times log n to the base p plus some polynomial in p and 1 over delta.
Taking only one.
So we are taking only one, yeah.
Only the big one.
So did you try just generalizing the arithmetic combinatorics results to replace sum by linear combination?
So I tried a little bit, not very seriously, but I didn't know how to really even get started. I was thinking about that even when I was originally thinking over the reals for the problem. I mean, can there be an additive combinatorics proof to rule out LCCs over the reals?
You can get a I think the first part you can get a conclusion about some multiple of
Even with linear combinations?
Yeah. Assuming linear combinations is the assumption, you can get a conclusion with linear combinations, and I don't know whether Rujo will apply.
This is really an assumption about graphs, right?
Yeah, this is a graph theoretic thing, but once you want to do the pigeonhole principle with the paths of length 3, you have to put the linear combination.
Yeah.
Yeah, and then they show up also in the conclusion.
You also lose a cutoff p.
It's not clear. No, it's not clear to me that you lose. So I don't know. I just asked if you try.
But try a bit.
But maybe interesting in itself, but it is additive structure if you have linear combinations.
Yeah. But Avi, just say the characteristic is large, right? And you look at a set with small coefficients, like Boolean coefficients.
Yeah.
Then you're going to have much of the set, adding together is going to have small coefficients over this characteristic. But it's not going to be contained in any small subfield, any small subspace, right?
So I'm not sure. You have a counterexample in mind, right?
Say that you look at say you take P, and you look at all vectors. The set A consists of all 0, 1 vectors.
Yeah.
And you add, so you look at a sum, it's going to be a 0, 1, 2 vector, and very concentrated on things with relatively few 2's and lots of 1's.
Yeah. So what?
So that's a relatively so that's going to be the set B that it's contained in.
Does it satisfy this? Does it satisfy the?
Is it saying that all
The
combinations?
size of B is about the square of the.
You're only looking at Russell. You're only looking at sums.
Okay, but say,
about combinations.
well, okay, but say, let's not do 0, 1. Just say in an arithmetic progression, so just like 0 up to V, and then the sums are going to be 0 up to 2B. Okay, if B is smaller than the. So
you are creating the condition of the BSG with the
So you're gonna get, if it's dimension d, you're gonna get like a 2 to the b is gonna be 2 to the d bigger than a.
But don't we want a BSG theorem where it's not just an
But
epsilon
you have
fraction
the-
of sums, but an epsilon fraction of linear combinations?
The condition
But
is for
here we
every
only
pair
know
there
that
is
there
a
is
linear combination.
one linear combination.
Yeah.
So the number of pairs for
No.
which there is a linear
Exactly.
combination in D.
Yeah. For many there exists a linear combination. It's but it's interesting.
Yeah. Yeah, in the graph theory lemma, it's important that you can write a sum as a difference in sum of several sums.
Yeah, but
That
you
it's
can
not clear.
normalize this sum, right? So that you'll get a conclusion also with linear combinations.
Yeah, but
Yeah,
they
so
will
like
always be different linear combinations.
yeah,
Right,
that's
right.
right. So you'll get into Ruja, you'll get a different condition. The question is whether it
Yeah.
applies anything or not.
Okay.
Yeah, that's all I.
The Sylvester Galai over the reals is the proximate Sylvester Galai is roughly what you're saying. For many pairs of points, there is a third point in their span, then the dimension is small. Right?
That's right. Yeah.
So we have this in the
Yeah,
previous.
that's right. But so that it's true, but it's not an arithmetic. It's not quite an arithmetic combinatorial.
Here
So
you
I
have
guess
a large number of pairs,
yeah.
not for every point, many other points.
Yeah, so it's possible that you need the right order of this quantifier, that for every point there exist many linear combinations of Q. Right, yeah, that's right. So yeah, some version of it is true.
Mm-hmm. So that's so I've not talked about multiplicities at all, but so what so I won't say anything, but what we basically end up showing is you take any LCC which has multiplicities, and you can take a puncturing of it. You can throw away. So if you have a delta LCC, you can find so you have a delta LCC of length n, then you can get an alpha LCC of length alpha n, alpha LCC of length alpha n, where alpha is something like some polynomial in p and 1 over delta. So you lose some fraction. So
You mean you can throw them at
you can throw away a lot of elements away and get a remaining, the result will be an LCC with weaker parameters, but each thing will occur with the same multiplicity. And then everything, all this will apply. So you do a lot of combinatorics with these elements which have high multiplicities. And then you use the fact that it's an LCC to show how to prune it away, to toss out some elements so that the resulting thing is still a weak LCC, but every element occurs with the same multiplicities.
So you cannot get rid of the multiplicities, but all the multiplicities will be
The same. And once they're all the same, then you just look at a scaled down version and apply, and everything will just go through. But that's also like, that's half the paper, the proof of getting rid of the multiplicities. That does give a lot of trouble, but it's not very interesting how to do it. But so there's no additive common, nothing. It's just mainly graph theory. You look at the graph where the edges, where you, on every edge, you write, for every pair where there's some, or there's some linear combination which adds up to something, you label the edges. So it's a graph with lots of labeled edges, and there's a lot of pruning and degree counting, and you're playing around with these graphs till you throw away enough vertices where the resulting graph is sort of regular in some sense. But it's a lot of effort, but it's not very interesting. And so you can throw it. And
There's another question I have about, or comment I have about the arithmetic combinatorics. I mean, you start from a stronger assumption than BSG and Ruja, namely that you have an LCC and you get a better conclusion about it because it's about the dimension of the whole space as opposed to the fragment. So the LCC condition is natural, but maybe there's another condition which is weaker. Nevertheless, it would fit into the arithmetic combinatorics framework, in which case you get structure theorem for the whole set, which will be interesting for these guys. So I'm just wondering what is the. I mean, anyway, it should be advertised. I think this part of the That I think is interesting in itself, not as the coding result.
Saying, can you write down sort of in a combinatorial condition that's sort of like the minimum that you're using in this argument?
Yeah.
It's weaker than being an LCC. And
so most steps we just use it. The
Yeah, I'm thinking condition that I'm thinking about. I mean, you infer from the LCC condition a condition about the number of pairs that are that whose sum is in the set or whose linear combination is in the set. But then, of course, when you amplify, you need
we
to
use
get
every
the
element had
LCC.
lots of pairs.
So, but still, there may be a
Right.
condition about
Right.
For every subset there are lots of pairs that
Right.
are in, or
Right.
something. Anyway, it's
Right.
something to think about.
I think that if it's not an LCC, if you have some coordinates that don't have many pairs that decode them, then already it's not true because
Yeah.
You can just have isolated elements,
Exactly.
maybe,
I
right?
think it's a required condition.
Or maybe just like with Sylvester
Yeah.
again. Yeah. Okay. More questions if we are into the questions.
Do you want to make a break for a few minutes?
Yeah. How about the 5-minute break? More questions.
So let me finish up by just saying that also
sorry,
I wasn't nothing important, but so just 3 query LCCs. So this was all about 2 query LCCs. So and now in 2 query LCCs, now we know that LDCs and LCCs are very different. So on different fields they behave differently. But there's the question of 3 query LCCs where nothing is known. Even in LDC, for LDCs, like the upper bounds and lower bounds are way off. And the only lower bounds we have from LCCs come from lower bounds we have for LDCs, which are also very, very weak. So the 3 query question is completely wide open and very interesting.
Just some small polynomials, right?
Some.
For
Yeah,
for
for
3,
three, yeah,
even
that's
for 3.
For 3 and 4 queries, it's n squared.
Yeah, it's just
Yeah.
squares.
So the upper bound for 3 is exponential.
The upper bound, so for
sub-exponential for LDC.
For LDCs, it's something slightly sub-exponential. For LCCs, nothing is known. For LCCs, I think maybe the conjecture is that you can do nothing better than what you did for 2 queries. All the way, you need the entire space. There's nothing non-trivial.
P to the root n.
Oh, P to the root n. Reed Muller will give you.
No, it means 4, right?
No, 3.
You can do it.
No, you take a degree to.
Reed Muller will give you P to the root n.
You take a degree to Reed Muller code, right? You decode
It would be exponential in the power, right?
And over the characteristic 0, there's not.
Even agree to, you don't agree
Yeah,
to
good.
the-
Over characteristic 0, nothing is
Maybe
known,
not
right?
four,
Yeah,
but
good.
then you need 4 queries. I don't think with 3 queries you can get anything which is closed.
I think,
you can.
I'll leave you the 3 versus 4 argument for lunch.
Okay.
Thank you.